Do not look directly at the sun. The sun is bright, and our squishy, liquid-filled human eyes have evolved for use in an average solar irradiance environment. That's a mouthful, but the lesson is simple. Do not look directly at the sun, even using sunglasses. Doing so can permanently damage your eyes and your ability to see. In extreme cases, you may become permanently blind. There are safe ways to look at the sun, either by reducing the total light that we observe with our eyes or by narrowing the spectrum of interest into a short range of colors. Common light-reducing tools are the number 14 welder's glass or an astronomy-specific pair of solar sunglasses like these. Now that we're finally equipped to look at the sun, let's go ahead and have a look. Wow. The sun's surface, which is called the photosphere, is a roiling inferno of activity. Bright patches model the surface, separated into small cells by darker boundaries. Once in a while, you encounter a very dark patch, a sunspot. And if you look closely, you can also see hot gases above the sun's surface, following magnetic field lines. Every detail we see on the surface of the sun is the result of the thermonuclear reaction at the core. The photons that eventually escape from the surface of the sun are not the same ones that began the journey in the nuclear furnace at the stellar interior. Although the energy was produced by fusion, that energy went through several stages in its 100,000-year journey. The most notable was the journey through the convective zone, where our photon's energy was locked away in the vibrations of the hydrogen and helium gases as they floated to the surface. Once exposed to the vast vacuum of space, the heat energy contained within those vibrations can now escape freely as photons. Since these photons originate from hot, dense gas, they're mostly the result of blackbody radiation. Some sprinklings of atomic hydrogen emission and absorption are present in the sun spectrum, but the dominant component of the spectrum is the result of the sun's surface temperature. Since we can measure what the peak wavelength of the sun's blackbody emission is, we can use Wien's law to calculate the average surface temperature of the sun as well. Since the sun's peak wavelength is about 500 nanometers, which is to say a yellow-greenish color, we'll plug that number into Wien's law in order to calculate the surface temperature. The sun's surface temperature is equal to Wien's constant 2.898 times 10 to the negative 3 divided by the peak wavelength 500 nanometers, which results in a temperature of 5,796 degrees Kelvin. The fact that the sun does not look green, when in fact it has a peak emission in the wavelength of green, is due to the fact that the sun also emits a lot of red and blue light. And when you combine red, green, and blue light, we observe it as a white light. But what about the strange pattern on the surface of the sun? What causes this pattern to emerge? These are called solar granules and are the result of the convection in the photosphere. Hot gases rising from the stellar interior are visible as bright patches of yellow. But what happens to them once they're at the surface? At the surface, these gases emit light and in doing so, cool down. The cooler gases are now more dense and therefore less buoyant, and they begin descending in the zones at the boundaries of the hotspots. These cooler gases are visible as the grain-like boundaries on the sun's surface, and this is where the cool gases begin their descent. The sun's photosphere is a layer of gas that becomes cooler in the outermost layers. This image of the sun's visible light shows all the colors of the rainbow and corresponds to blackbody emission from the lowest region of the photosphere. As the light travels outward through the photosphere, some of the light, with special colors, is absorbed by the cooler hydrogen, gas, and other elements present in the atmosphere. When the light is absorbed at these colors, we see black lines instead of that color. We call this an absorption spectrum. The sun doesn't just produce good old-fashioned visible light. Wien's law tells us that it also produces high-energy UV radiation and X-rays too. These images come from NASA's Solar and Heliospheric Observatory, called SOHO for short, and show the sun at wavelengths that our eyes can't see. This image, for example, was taken with a peak wavelength in the ultraviolet, or 19.5 nanometers, revealing even more of the stellar atmosphere that was visible to the naked eye. Not only that, but in the UV, there's much more contrast, so activity in and above the photosphere is much more apparent. The outermost regions of the sun's atmosphere are called the chromosphere and the corona. The corona is much hotter than the sun's surface, which scientists think is a result of the tremendous energy contained within the magnetic fields that are generated by the sun. The energy produced at the core of the sun is the same energy that nearly all of life depends on. From the water cycle to the web of life, the majority of the energy required to sustain all plant and animal life on Earth comes from the sun. The energy that we release when we burn hydrocarbon-based fuels can be traced back through geological time to a moment when an ancient plant absorbed light from the sun, which eventually contributed to coal seams and oil wells where we derive the fuel for our modern life. This is contrasted by modern renewable fuel sources, like solar energy, that convert direct sunlight into electricity. In a sense, almost all energy sources can be considered solar energy. We happen to be in a relatively stable energy environment around the sun. If Earth were closer to the sun, like Mercury and Venus, it would be much too hot for life to exist as we know it. Similarly, if Earth were farther away from the sun, like Mars's orbital radius, it would be much too cold for most of life to survive. Asking where a planet can have liquid water, or more importantly, the conditions required to sustain life, is a fundamental question that many scientists have asked throughout human history. Astrobiologists, people who study both astronomy and biology, call this region the habitable zone. Generally speaking, the habitable zone is a region surrounding a star where a planetary body like Earth would be able to support liquid water. There's some flexibility in this definition, since it would include frigid planets where the maximum temperature is just above the freezing point of water, and intensely hot planets whose minimum temperature dips just below the boiling point of water. Let's look at our own solar system and see where we would draw the boundaries of the habitable zone. Scientists believe that our own solar system's habitable zone extends as close to the sun as Venus, at just under 3/4 of an astronomical unit, to as far as twice Mars's orbit, or twice 1.5 AU. Arguments vary regarding what we consider normal life, since we have examples here on Earth of extremophiles that can live at extreme temperatures. So we'll just have to leave the boundaries of the habitable zone as what they are, estimates. What if Earth were in orbit around a different type of star, instead of the G-type star we currently orbit? An M-type star, like our nearest stellar neighbor Proxima Centauri, are cooler red dwarf cousins of our own sun. Since they have a lower surface temperature, the habitable zone around has to contract to smaller distances. If Earth stayed at the same distance from an M-type star, like this, it would quickly turn into an icy snowball at the edge of the new habitable zone. On the other hand, if the sun were suddenly replaced with a more massive and therefore higher temperature star, like a blue blazing B-type star, Bellatrix, the habitable zone would move outward in the solar system, leaving Earth a burnt crisp. Similar effects can happen as stars age as well. As stars move off the main sequence, they enter a series of stages where luminosity and radius tend to increase. We'll see more about this in the next section.